So that's kind of where we are going to be today. So, all right. So let's go ahead and start. Again, the first part of the lecture, I'm hoping go over this requirement. The second part, some calculation, a little bit of calculation here. So, special purpose outlet. You guys did a special purpose outlet yesterday, right? You did a pump. We have some pump that we said the special purpose outlet that could be 120, 240, say 15 amp, 20 amp, just special for a certain purpose. And as well as water heater. You guys did the water heater yesterday, right? You laid out. So we're going to do calculation about the water heaters and a few things about water heater. So basically, a pump and water heater. That's the topic, and these are directly related to what you guys done. We did a sump pump, but this talks about a water pump. A water pump. So moving on. Okay, let's go here. Okay, so a few things I would like you guys to do. I don't know how many of you guys have wired. There are two types of pump they use for the water. If you live in a rural area and you don't have city water, you have to pump your own water from a well. So what they do is anybody have seen them or lived in, you have jet well and submersible well. And very common in rural areas where you have your own well. So we're going to talk about how to install these jet well and submersible well. It really nothing, it's almost like a sump pump, except the use is different. So these are what we're going to be covering: sump pump, jet well and submersible pumps. Electric water heaters. We're going to have a water heater. We're going to design a water heater calculation requirement for water heater, electrically speaking. So pumps and water heaters is the topic for the day. Then because pumps, guys, are motors. When it comes to motors, we're going to do I know you guys did it with Gary. I'm going to review residential today, single phase, and we're going to do intensive calculation for motors, because that's everything that we install in the building in the motor. So we start with the branch circuit, conductors, cable, raceways, motor short circuit protection, disconnect for motors, overload. All these topics for motors, we want to talk about them, as well as grounding, So for these motors. There's also a different type of meters, guys, they use in this chapter. By the way, this chapter is long. A lot of information is about water heaters, scalding, and so read through the information that's not electrical, just FYI, and pick just the electrical stuff. So they talk about time meters. When we talk residential, when we talk commercial, we'll talk different time. But when we talk about residential, guys, they have time of use meters. The utilities wants to. You guys are familiar with the grid. The problem with the grid is if it peaks at the same time, it screws up the amount of energy that they can distribute to everybody else. So if I can control the way you utilize energy, I can produce less energy and distribute the energy more efficiently. That's why utilities have, you guys are familiar with the safety switch typically we use with the air conditioning, right? That's saver switch. Saver switch that we use, not safety, saver switch that we use with air conditioning. That's exactly what they're talking about here, the time off use meter. We'll talk about these. Voltage variation. What happened? What's the acceptable voltage? When we say 240, Aaron, you rarely will ever measure a voltage and you find a 240 in a house. So there's plus or minus, as we always say, 10% acceptable range for water heaters and motors. This is, I'm not going to touch too much on that one. If the water is so hot, scalding and protection from scalding and all this good stuff, that's basically part of the water heater control system that they have. Some pumps, the pump water heaters too, heat pumps. I don't know how many of you guys have seen a heat pump, the concept that they use a heat pump to heat the water. Anybody have installed a heat pump? Heat pumps, we'll talk a few things about the heat pumps. Okay, any comments? So the topic will be submersible pumps and heaters, basically. Any comments, guys, before we go ahead and start? Okay, so if you live in the metro area, you probably don't have a submersible pump or a jet pump, because we have good pressure and we have city utility, and you get your water. You don't have to worry about these ones. Typically, these are in residential areas where you can have submersible pump. There are two types. There's the jet and the submersible, and the submersible is the most common pump that they use. We'll talk about we'll go directly into this one. This is the jet pump. Anybody have installed a system like this? Okay, you installed this one. The way the system is, you have to have a pre-charged water tank here for the system to work, mechanically work. Electrically, let's talk about electrically first. Electrically, for this system, we have a pump right here. So electrically speaking, what do I need for a pump? I need an overcurrent protection device, and I need to come over here and feed from here the overcurrent protection device and down in here. So this will be my controller. The switch will be my controller. My overcurrent protection device is here, and most likely you'll have a disconnect, some type of disconnect within sight of it, or if the circuit breaker is not there. So I have an overcurrent protection device. I have a branch circuit, that's electrically speaking, coming to a disconnect into the controller and down into feeding the motor. That's what we care about, electrically speaking. Everybody's okay with that one? So we need to size the overcurrent protection device, the branch circuit, the disconnect, the controller. In this case, it's very simple pressure switch. And the motor, we wouldn't size the motor. So that's electrically speaking. Now, mechanically speaking, the way this works, you can see the pressurized tank, guys. What they do is the impeller here, it pushes. You have to fill this pipe in order for the system to work. That pipe, so it pushes that water downstream so fast that as it pushes it fast, that jet, that's where the jet effect. It pulls the water out of the well all the way up into the tank. It keeps going until you hit 40 psi. And then when it goes below 20 psi, I believe, it trips. So it keeps charging the tank until you hit a pressure of 40 psi. You fill it basically. Then that pressure switch will open because it's pressure activated. It's looking at the pressure here. When it reaches this 40 psi or so, it will open, de-energize the circuit. Then you keep taking all the water until you hit another pressure, which is 20 psi. Then closes again and does the cycle itself, right? So you don't turn your submersible pump on and off, do you? This is regulated, self-regulated through a pressure switch. Any question, guys, about that? So the components are, you have a dry pipe. That's where you shoot the water so fast that it pulls here so fast as it goes through this angle that's called the jet. It pulls the water out of the well, and that's exactly what you want. And it dumps most of it in the tank. Some of it continue to do the whole jet effect. So you have the jet, you have the foot valve here, strainers. I have a couple of things, a drain pipe, suction pipe. That suction pipe that brings the water to the tank. So you shoot the water, a very small amount of water down so fast that with this jet effect, it pulls the rest of the water into the tank until it hits 40. Stop because of pressure switch. Then we keep consume power until you hit 20. Start again, and it keeps going over and over and over. Any question? So you don't need to know how the system works, but guys, when we, as electrical engineers, the more we know about the mechanical system, the better we will be, right? You agree with me? When I started doing design, I don't know how many of you guys know the interface between, later on, we're going to talk about rooftop units. That's one system. We're going to talk about cooling tower, chillers, air handling units, boiler. How does the system is put together mechanically? These are not electrical stuff. We don't specify cooling towers, but we have to power them. So it's really good to understand how the system works, so you can be informed when you design the electrical system for them. Same thing here. We don't need to know how it works, but if we know how it works, we will be better off understanding how to size it. Okay? Any comments, guys, about this? So what's our involvement in this business? What is our involvement? Our involvement is, number one, you need to size our protection device. Number two, the branch circuit. Number three, a disconnect. Number four, a controller. And most of the time with the controller, guys, not at this, you will have a little overload here. Number five, you have an overload. So that's basically our involvement in it. Any comments, any question about this, Jet? Any comments, any questions? So that's basically, I want to do a calculation about the electrical stuff later on. Submersible, so these, I want to bring to your attention, guys, look where the impeller and the pump itself is located above the well. Here's the well. This is the jet pump is above the well. The most common ones, actually, it's called the submersible pump. They're inside the well. Here's how they look like. So the two technologies. The jet well, you put the pump itself above the well. The most common ones is submersible pump. Can you guys see where they put the pump right in here with the impeller? What's our involvement? I always like to start with our involvement. Our involvement is overcurrent protection device we have to provide. So here's number one. Number two, I need a disconnect. number 3 in branch circuit, right? I have some type of a controller, so I have to have a controller here. This is number 1, 2, 3, 4. And with the controller also comes an overload, number 5. So these are where we can get involved in the sizing process. Make sense? So that's, now how does this work? The same thing, guys. Instead of the pump is actually right here. It sucks the water up into a tank. When the tank reaches a certain pressure, 40, there's a pressure switches here. A pressure activated switch. It will de-energize the circuit. The controller stops the pump. When it goes below 40 or so, 20 or so, it closes and closes, right? We know what the pressure switch. Did you guys wear a pressure switch with us in the lab? There's a couple of pressure switches. They open and close based on the pressure. So these are, so this pressure is, so it continues. This is normally, what would that be? Normally closed contact, and when the pressure reaches 40, it pushes it to open and stays open by design until the pressure goes below 20 by design, and then it closes again, and it keeps doing it, right? That's your controller, self-controller. So you can see all the components that they have. They have your controller here, your switch, your pressure switch, that part of your controller. I will bring your attention, guys, this is submersible cable that they use with it. And the rest is all these systems to make the system work, all these mechanical systems. Any comments, guys? Any questions about our involvement and how does this work? It sucks, the impeller is right here, sucks the water right through here. There's no jet, there's no 2 pipes like the other one. There's a jet pipe and a sucking pipe. This one's only 1 pipe. It pulls it all the way up to the tank, and the tank, that they call it pre-recharge tank. That's the one that regulates the on and off for this pump. Any comments, guys, about the submersible pump? Again, the most common ones. I grew up actually with one of these too. So really cool stuff. Any comments? Any questions about these? So knowing, our job is just to know. You can see at the bottom of, there's a lot of issues, guys. Typically, we don't install the pumps or the wells and all the stuff. They put them together. Somebody else will put them together. And our job would be to, most of the time, it's a complete standalone system. Really, we bring a feeder to it with a disconnect, you know. When it comes to mechanical equipment, guys, it can be as easy as, our involvement in the mechanical equipment can be as easy as providing an overconduction device and a feeder, conductor. A lot of them are, and then everything else is provided by a third party, right? Or as complicated as we add all the control part and of course the pump buying plus the cable in between, which is typically we don't do that. You know, typically these are third parties provide all these wells and so forth. Like air handling unit, our involvement in the air handling, do we specify the air handling units, the size of the air handling unit? We don't. As a matter of fact, the controller for the air handling unit, we have no control over it. What we do is we do 3 things. We provide an overconduction device, a feeder, and a disconnect right next to it if the manufacturers don't provide that disconnect. Cool? Any questions, guys, about these? Can I have thumbs up, Chad? We know how it works. Cool, and we know what we need to okay, so later on, guys, I'm going to do some calculation about the electrical stuff that we need to know about this pump. That's all. I'm going to come back to these, guys. These are the articles that size the overconduction device for motors. So I will come to this table later on and do a couple of sizing. Overload, when we have motors, guys, you're going to see later on, I'm going to do an example about overload, and we size. For motors, you have to have an overconduction device for short circuit and overload to protect the motors because they're so expensive. So the overload, typically we size them 115 to 125. Well, I'm going to have an example in a second here about these. Disconnects. Motors are rotating machines. We got sick of people losing their fingers inside machines, right? Chopping their fingers and all this good stuff and being killed. So the Smarter Than Chad decided we needed to have something physically, mechanically isolate the whole system. After you kill the system through the pressure switch, you need to go to a disconnect like this one on the wall, guys. And if it's on, you can very clear it's on now. You can put it off, lock it, tag it, and do your work on equipment. Safety. The one who lock it, tag it, or work on it could be an electrician, or it could be a mechanical contractor, or could be a control guy. So it's not just the disconnect, is for a lot of other disciplines. Okay, we'll talk about the disconnects, guys. Um, so we'll talk about them. Typically, the disconnect, we size them based on 100, 1.115 times the full load current. We'll talk about these in a second here. And the disconnect have to be within sight. And within sight means no more than 50 feet, right? Within sight, no more than 50 feet, no obstacles. So I don't have to jump over something to reach it. Within sight, typically it's right there within 10 feet. Most of them, guys, are within 10 feet of the equipment to put a disconnect. But the code allow you up to 50 feet. Any comments about the disconnects for safety and so forth? Grounding, everything for the submersible pump and the jet pump have to be grounded. So when you pull, you're going to pull, if it's a 240, 2 hots, and 1 conductor, equipment grounding conductor, right? So that's basically what you need to do. Sometimes even right next to the well, guys, what they do is they drive a ground rod and to the frame of the well, the submersible well, you tie it there. But either way, you have to pull an equipment grounding conductor with the pumps that you're going to be using. Any question about the pumps, guys? What I owe you later on is I'm going to do an example, calculation example, just to refresh your mind about the disconnect, the overcompression device, and so forth. Can I get you guys to understand a pump is a motor? A motor need the following: need an overcompression device, circuit breaker, need a conductor branch circuit, which is a conductor, need a disconnect for safety, and an overload, and a controller, so it can control the system. Any comments, guys, about submersible pumps, which is a motor? Can I have thumbs up, Chad? We know it. So please read this one, guys. Again, we're designers. The more you know about the different electrical equipment, the better you will be. The second thing is water heaters. Now motors, as we all know, submersible pump, because they're motors, guys, the article that talks about them is Article 430. And we're going to spend some good time, and you see, we'll talk about Article 430. Now, we'll get back to it. Moving into the water heater. Water heater are called appliances. Appliances, there's the NEC code book have article called 422. This is the article that talks about appliances. So there's two different articles, appliances and motors. Water heater sizes that you can do. Here's the typical sizes that we do for water heaters that you can use. Most of water heaters are resistive load, though there is inductive load. Resistive load, so you have a resistor, you heat the resistor. Anybody have an electrical water heater? Not a natural gas water heater. Electric water heater, it's resist, so simple. You have multiple resistors, you basically turn them on and off to control the heat inside this water heater. Really not a whole lot to it. Typically, there are two of them. Now, let's talk about electrical, and then we'll talk about the mechanical part. Talk about the electrical first. Our electrical involvement is going to be with the following. I have an overcurrent protection device like you did, and I need some type of a disconnect, and I need to tie it directly here. So here's number one, right? I need number two is the branch circuit, and number three is the disconnect. This is typically what our involvement, this looks like it, Chad, our involvement with number three. This is what our involvement, guys, with a water heater. You did it there for me yesterday. What did you guys do when you when you circuited your water heater? You have to provide an overcompression device, typically 30 for dwelling, 30 amps. Branch circuit 2 hots only because it runs at 240. So you branch circuit of 10-2, right, with a ground, and a disconnect unless the overcompression device is within sight of the appliances. You have to provide a disconnect. And then typically, so up to here, and then typically, guys, they have a flex. Anybody knows why they flex the last piece? They flex it. Ease of installation and movement and maintenance, and so they have a little piece of a flex here. So typically, this will be an an NM cable up to here. Then you change it directly to a flex or a cable, any type of cable that you can use for ease of installation. So that's our involvement, electrically speaking. Any question about our involvement before we talk about how the system works? That's our involvement. I want to bring to your attention, guys, a couple of things. This is the article that's 422.30 that requires a disconnect for us. 30, yep. And this is where it tells you that disconnect can be out of sight as long as it can be locked in the open position. Now had we Had we had circuit breakers in our panels that can be locked in open position, we could have avoided putting a disconnect for our water heater. But typically, guys, load centers that we have, you can't lock them in an open position with a permanent means. Typically, they don't come with this. So that's why we provided a disconnect. But there's an alternative way there in where we could have avoided the disconnect and have a circuit breaker with a mechanism of locking it. But it has to be there at all times, not portable ones. You have to have an equipment ground conductor with it, and the flex cannot qualify, especially if there's limitation up to 20 feet. If you're using a flex, the flex can't qualify as an equipment ground conductor. If it's more than 6 feet, and if the overconduction device is more than 30, which is 99% of the time, your water heater is minimum of 30. So you still have to pull an equipment ground conductor with your flex. Any question guys, electrically speaking? Can I have thumbs up, Chad? We know how electrically speaking this. Now, I want to remind you, is there anything motor, any rotating objects here? So this is what they call it, non-motor appliances. Is this a motorized appliances? Does it have any motor in it? No, right? There's nothing in it. It all it has is a heater. Okay, so that's electrically speaking. Now, mechanically, how this system works, they have two heaters, guys, right here. One heater can give you the base heat, and the other one is if you and every one of your 10 children. Brian, do you have 10 children? If you're 10 children, your wife and you are taking showers and at the same time in 10 bathrooms, so you're using all the water. Now exaggerating here. If you're using a lot of water, one of them. So I think the lower one will give you the heat, the base heat. The upper one will come only if you need hot water fast because you're using a lot of hot water. All this stuff is regulated with the controller that comes with it. Water heaters, guys, you have controllers over here that typically comes set by mechanical, by the plumbing guys and so forth. So our involvement in it is really limited as electrical. So two of them, one will give you a baseline hot water, and the other one gives you more hot water as needed. Any comments, guys? Any questions? Any comments? Any questions? And the way there are pipes over there. Put them in the water. You heat them. You heat the water. That's it. And then you keep one comes in, the cold and the hot pipe, and then you circulate the cold water, the hot water right through the building that you have. Any comments? Any questions? Comments? Questions? Okay, so that's basically what we have for the water heater. We'll talk about sizing for water heater in a second here, guys. Then the rest of it talk about scalding water and all this stuff. Could you please read this one? It's try to avoid reaching a temperature of 120. There's a lot of control issues, guys, in it, so it doesn't give you very hot water. It shuts down. There's a lot of safety issues. If the water gets so hot, it shuts down. There's valves that if it turns into steam, it opens the valve, and the worst thing that could happen is you change water into steam. You basically created the steam bomb. Everybody knows that? And fast, bam, explosion. So there's a lot of safety when it comes to messing with water. You don't want to change water into steam. Steam expands so fast, creates explosion. So there's a lot of safety. Two things here. First, you don't want to change it to steam so create a bomb, basically. And number two, you don't want to get it too hot so you can burn the peoples. So there's a lot of control involved in that. You guys will read it at your own. Most of them are wired with 240, at least here in the US. When we size branch circuits, we size them based on 125% because it's continuous load. We assume it's continuous load, and we size them based on 125% the branch circuits. The overcome protection device, we size them slightly different. I'm going to show you where we size the overcome protection device for these and have an example. So branch circuits based on 422.11e, how to size the overcome protection device. We'll go and look at this one in a second here. So 240 resistive heat. Okay, a couple of things here about voltage variation. This is on any system. I want you guys to remember this one little thing. Here's what NEMA assume that your equipment can function properly based on plus or minus 10%. So take this area. If I have a water heater or a pump and my pump or water heater is supposed to, the nominal voltage is for 140 volt, single phase. Okay, so if I go 10% higher, so what's 10% times 140? Anybody has a calculator that get me? So 1.1 times 240, 264. So I have, this one will get me, in this case, I'll get me 264 volt, okay? Now, the same token here, if I have minus 10%, so this is plus 10%, meaning extra 10% of the voltage. Okay, how do you make a minus 10% on a voltage? Basically, take 10 out of 10% out of 100%, I'll get 90. So 0.9 times 240, what do you get? Geniuses here? 260. 260 volt. So this is, what this is tell you, the appliances guys supposed to function properly between this voltage and this voltage. Now, Kerry, why do you think this is very important? Because you can't maintain a constant voltage, guys. Voltage is never constant. We have a nominal voltage for calculation, but the actual voltage always fluctuates. If the air handling unit runs right now, the voltage will go down. Shut down the air handling unit, the voltage goes up slightly. So the smarter than Chad have to allow this fluctuation, the fluctuation 10 plus or minus 10. I want to remind you that's the extreme situation, but when the code, you guys remember what the code allows? Anybody can remember what the code allows you? Voltage drop. That has to do with the voltage drop too. What's the maximum? 3%. Well, with a branch circuit, 5%. So the code has to go half of this. The code wants to force you to do it half of this. So what's the code? This is plus or minus 5%. Right? So that's where the voltage drop, usually minus, of course, the voltage drop. So this is what we designed based on 5% less voltage for our equipment, and the manufacturer allowed 10%, so that we still have area of caution of safety. Does that make sense? Does it make sense? Where the equipment, here's where it functions, here's what we designed, we're almost half of what we're getting even more stringent in our design. Does that make sense, guys? So if I have a piece of equipment here, and the piece of equipment is rated for 240, I can tie this piece of equipment to the 240 system, knowing that if the voltage goes this or this, I'm still good. The equipment is going to function. Now, what happens if you go higher than that? Your equipment will malfunction, not work efficient, die prematurely, depending on how high you go. Double the voltage on the equipment, you burn it instantly, right? Go 50% on it, you also burn it instantly. Go 25, you cut its life probably by half. So I mean, so the higher you go in the equipment or the lower, the more you cut its life by certain value. Any question about these guys? The variation of voltage? Can I have thumbs up? That Chad, we know that the voltage does not stay constant and varies. Okay. The last thing, guys, is heat pumps. Heat pumps, I don't know how many of you guys have seen a heat pump. Heat pumps is a reverse function of air conditioning. Take your air conditioning. What does the air conditioning do, guys? Everybody knows what the air conditioning does, right? With the refrigerant. We'll talk about this cycle when we go to the air conditioning. The air conditioning, it takes the heat, it collects the heat from your house, right? Through the refrigerant, and takes it outside through a coil and throws a big blower throwing air right through the coil. What do you think why the blower outside is blowing all the time? They're blowing air through the coil and picking the heat out of the coil and throwing it to the Lord outside. Okay, remember that? Have you guys stuck your head one time above the air conditioning and see how hot it gets, right? The outside unit. Anybody put your hand there? You see how hot the air, that heat is coming from your house. Take this heat that's thrown outside and channel it and put it into the water heater. So what do you get? Heat. That's how they do the heat pump. Looks like exactly like an air conditioning, except it's reverse function. And instead of taking the heat out of your house, instead of taking it and throwing it outside, it takes it, channel it into the water heater. Of course, you have to have a special equipment to do that. And then it heats the water. You heat the water with it. Now, I want you to understand, you can't have it alone. So this will be supplemental heat. So in the summer, when your air conditioning is running, you can have an electric water heater supplemented by some pump. So when you're not exhausting the air out, the hot air out, you can run the resistive heat and up and running. Cool. Now in the summer, when you exhaust the heat out to cool your house, instead of taking the heat out, what do? Throw it outside. You channel it down and heat the water in your house. And by doing this, what do? You reduce your consumption of electricity and you cool your house at the same time. Does that make sense, guys? So it looks like an AC unit and size like an AC unit. So that's basically, here's where they say 50 to 60% heater can 50-60% electric water heater save energy, because now you're utilizing the heat instead of creating the heat. You're utilizing the heat. It's like geothermal. If you've seen geothermal heating, guys, ever done geothermal? The temperature of the earth, was it 20? I think it's constant around 20 or.
It's more like 50, like 57 degrees. It says
20 Celsius. I'm sorry,
yeah,
I'm thinking
like
Celsius. Yeah, when I say 20, I mean Celsius. Yeah, so like about that. So 50 Fahrenheit, and when you grab it now with that 50 Fahrenheit, not 20 Fahrenheit, 50 Fahrenheit or 20 Celsius around this, you bring it in. That's, imagine in Minnesota, especially in Minnesota, if you have it, if you have below, that give you a big chunk of heat right into the house. You still have to supplement it with electrical or gas.
That's usually where the heat pump comes in, though.
Yeah. Yep. Any comments, guys? Any questions about this? Okay, so that's basically the heat pump supplement for your system. Let me go here. Slide a couple of things. Disregard Chad. Go here. Okay. Let me see if I got these here. Okay. A couple of things, guys. We went through the jet pump and we talked about how that works, right? So that's good. We talk, here's our involvement. This is always my favorite because this is our involvement. We have an overcome protection device, that's B. We branch circuit C. We have a disconnect and overload in D. We have a controller E and the wires in between. That's where we get involved, right? This picture indicates our involvement. So we have a 240 panel, 20 amp 2-pole circuit breakers. We have 12 conductors, and we have 2-pole disconnect switch right here. And we have 2-pole pressure switch. That's E to control it, and F we have the horsepower. This is summarized as a pump, a typical pump. Our involvement is in our own involvement here would be find this, size this, and sometimes we even get size into the disconnect too, and the wires in between. Thumbs up, Chad. Cool. Okay, so that's basically what we're gonna do. We talked to guys about the submersible pump, right? My submersible pumps and the cables and all stuff. I want to bring your attention for the submersible pumps is the cable. Look at the cables that they use. Suitable for use with submersible pump. Not any cable you can use in the well. Can you guys see? So it's all the way to the bottom. Centrifugal pump drives the water upward. Squirrel cage induction motor at the bottom. Well casing and all the stuff. So that's your submersible pump. This is really nice. This shows, I want to emphasize that one because it shows a few things. This is how we wire a submersible pump, typically from a dwelling. Okay, so look at this one, guys. You have the controller and the disconnect here. Your controller disconnect. Then you take your cable, an underground conduit or UF cable, all the way to here. Now, right in here, you need typically, depending on the pump, if it's even if you say 12.2 plus ground, right? 12.2 plus ground. If it's a 20 amp circuit, UF cable direct buried or put it in a conduit. Right here, you tie the frame to the grounding conductor. The casing of the well have to be tied to the grounding conductor, right? The disconnect, guys, does not have to be within sight of the pump. How are you going to put a disconnect within sight of a pump here? Pump is way down in the well. So they have the disconnect within sight of the controller outside. Any question, guys? So typically that's how they wire it. Any comments, any questions about that one? So that's your wiring. We talked about the water heater, different elements. Here's how they do the water heater, guys. Based on how you connect these two, you can get 380 or 117 So different sizes you can get from them. The last thing I want to talk about, guys, here is meters. Remember we talked about the meters? So if you can go with me quick to these pictures, please. So this is a couple of pictures in the back of your book that talks about meters. So let's just look at the first one. The electrical load, the water here, guys, is a big load, electrical load. So what the utility wants you to do, if they can coordinate the consumption of the bigger loads, they don't care about your lights. They care about the water heater, because the 5 kW load is a big chunk of K load. On average, your house cannot consume on average more than 10 kW. The water heater can be half of that. Can you believe that? Or at least a quarter of that. So they want to regulate air conditioning, water heater, what else? These are range. These are the major consumers of energy, the offenders in terms of energy. If they can regulate it, meaning they can turn yours off and mine on, and vice versa, they can reduce the overloading of the distribution and transmission lines, especially distribution lines. Because of this, they give incentives for people. How they can't force you to do that, they have to give you incentives. One of the incentives, they call it off-peak. So what they do is they have 2 meters. This meter is dedicated for this bad boy because it consumes 5 kW. Let's just say it's a 5 kW, a lot of power. So they give you a meter and they charge you lower rate, much lower rate than this meter. So 1 meter for everything else, 1 meter for the water, and they charge you less. But in return for charging you less, they can control, can you guys see that little contact here? They can control, set this contact to close at a certain time. They can control when you can use these appliances. Did you guys hear about smart metering now? That's what the whole green energy and green grid smart metering, that's what they're trying to do. They can if they can control the first of the major offenders in a house, then they don't have to build more nuclear plants and more coal plants, because they can regulate the transmission distribution system for the utilities. That's a big deal now. So if they can control this one. This is what it's called off-peak. So, for example, midnight when nobody's turning power off, they can turn it on, heat the water at night. They can turn it off when people come home around 5, say 4 to 7 o'clock, 8 o'clock, 9 o'clock. This is peak. It peaks up. In the morning when people get up, in the middle of the day when factories are running, these are peaks. Morning and evening are peaks. So they don't want you to run them in the early morning and in the evening when everybody's trying to cook and so forth. So if they can regulate the running, they can give you a better rate. Off peak.
We use that mainly because we got that for our air conditioning.
Okay, now what you get for air conditioning is not a different meter. You have a saver switch. Do you have a meter?
Yeah, they're able to cycle our air conditioning whenever they want.
But not with a meter though.
We have a separate meter.
Separate meter? Okay, I'll show you. The one that I have doesn't have a meter. It's just a switch. Radio frequency control. I'll show you. The second example actually is exactly what you're just saying. This is a separate meter.
Really small little guy, plastic.
I gotta look at it again because
Yeah.
they came out and yeah, you're gonna charge them cheap, go ahead.
So that's basically this meter. Here's what you probably have. Another thing, guys, they do is, this is typical for air conditioning and could be for waters, is the utility will come over here and you feed your 30 amps right in here. You bring one of the hots into a relay, and this relay is controlled by radio signal. So what happened is, this is typical for air conditioning. I have this one in my house. They come and set it up for you outside for your air conditioning. And when it peaks, only when it peaks, they don't control it. They monitor the grid, like in a hot summer day when everybody's running the air conditioning and the grid is about to peak. What happens if the grid peaks? They start brownouts. They start shutting down feeders. Otherwise, the whole grid will collapse, right? Or a section of a grid. So instead of running brownouts, City of Bloomington now going to shut you down for an hour, and then Richfield after that, and so forth. Instead of doing that like in California, remember the brownouts? They say, we're going to shut your air conditioning. So they go to your neighborhood. Half of your neighborhood, say if you have 16 or 20 dwellings on your neighborhood, in your immediate neighborhood, they put 10 of them on at one time and 10 of them off another time. They cycle in 50 minutes. How do they control this one? With radio frequency. They turn them on and off. by turning half of them off. So imagine, so here's 5K. Imagine if I have 20, what would that give me? 5, 10, 100? 100 kW. This is my neighborhood just for the water heaters, 100 kW, okay? Now imagine if I cycle them, I turn them on and off not at the same time, I control them, cut this by half, so it'll give you 50. Now the grid have to provide 50 kW instead of 100 kW. Just for a short amount of time, guys, remember, then the peak goes down. Just short the peak for utilities is it goes up and then there's a base. It doesn't go all the way. So here's your base here. Sometimes it peaks a little bit and it goes back. So we could be just talking about 2 hours. We could be talking about 1 hour, 2 hour peak. Can you have thumbs up, guys? That's how they control it. That's another way of controlling it. So if you don't have to control it, this is how we typically do the water heaters. At least a lot of places, there is no control. It basically brand circuit, no control. In this case, we have another meter here that you can control it too, like we did. Okay, so either you have the relay that control it or a separate meter. Either way, you give him a full control over your offenders. Any comments, guys? Any questions about that one? 2 ways: a separate meter controlled by utilities or a separate relay controlled by the utilities. By giving you the relay, by what's in it for you, because now they are not metering it. Like in my air conditioning is controlled. What's in it for me? During the summer, they give you a reduction. If you enroll in this, like they told you, they will give you a reduction in your consumption within certain amount of months. Typically here in Minnesota, summer months, three months of the summer. If we have summer sometimes. The rest of it, guys, just information about skating and all this stuff. Please read through it and don't worry too much. This is my favorite. What happens if the voltage goes up and down? What happens to the full-time current and the starting current? This is a big deal, guys, as we go. This one, I'm just going to mention that one a little bit here. So if I have a 120 system, here's my overcome protection device, and here's my AM motor, here's my 120 volt. Okay, I have a 120 single phase motor, right? And the voltage fluctuates with 110%. So we went higher. Look what happened to the current. The current decreases 7%. Now the current went down. To compensate for the higher voltage, the current drops down. Cool. And then look what happened to the start current. The start current increases. You increase the voltage, you have more oomph to start the motor, but to run it, the current goes down. The opposite is almost true. If the voltage goes down, to compensate for the loss of the voltage, what do you need to do with the current? Current goes up, right? And what happened to the starting capability of the motor? The starting capability of the motor goes down, okay? Because ultimately, guys, we're dealing with so-called P. P equals I times V, okay? To maintain, right? This is the power that you have. To maintain the same power, because the equipment doesn't care. If, for the most part, if the current goes up, what do you think the voltage is going to do? To a limit, goes down to compensate, because this has to stay constant. This has to stay constant, and vice versa. If the voltage goes up, what do you think the current is going to go? Down to compensate. For the voltage and the current, they have to equal. The power is constant. You have a 5 horsepower motor. It's a 5 horsepower motor. The power is not going to go up and down. What the motor is going to go. So take this. You have a 240 motor and you wire it with 120. Guess what's going to happen? You're going to get smoke out of it. Why do you think you get smoke out of it? To cut the voltage by half, what do you think the current is going to go? Double. Now instead of the windings are rated for 10 amps, you're dumping 20 amps in them. So they sit there, burn for a couple of minutes, but too much heat generated, and then that's how you get smoke. Does that make sense? So that's that formula. Really good, where it gets you by what happens to variation of the voltage on the starting current. The running current, you guys are familiar with it. That's what we did. The starting current is the oomph. Now, when you start a motor, guys, you need a little bit of oomph to be able to push the equipment, right? That's called the starting current. If you don't have enough starting current, your motor wouldn't start. It will run, but it wouldn't start. So that's why the more higher voltage you get, the better starting current for the equipment you get. But the starting current typically, what, 6 times the full load current, right? So just for 10 seconds, the equipment will suck 6 times more current than what it normally does, just for 6 seconds, to try to push that beast to start. Depending on windings and a bunch of other things, and the design of the motor. After 10 seconds, the current goes down to the full load current. Any question, guys? Any comments? Any comments? Any questions? Okay, I'm going to give you 5 minutes, and I'm just going to do one example about calculation, overcome protection device and so forth. Highlight a few things in the code, and then we'll go from there.
The waiver's done.